Now I'd like to welcome to the podium Dr. Rick Barto, who's a program manager at Lockheed Martin's Advanced Technology Laboratories. He'll be speaking to us about application of ICME in functional materials.
So I'm going to do something a little unorthodox and get to the conclusions first, because it's likely I'm not going to be able to hit all my charts in the 25 minutes. So first thing I'm here to say is I'm not a metals dude. I should be. I'm formally trained in material science, but I've forgotten everything I know about metals the day I walked out of my graduate school program. So I will say I think there's a lot my community can learn from this community in terms of all the work that's been done in materials genome and ICME. I wanted to make a few comments on the other speakers. Jim Warren has said emphatically the aerospace industry has led in this area. I'd like to amplify that and say not only is the aerospace industry led, but I think the Air Force Research Labs has led, as well as some of the other agencies, DOE, NIST, ARL among them. But Air Force, I think, has really put a strong stake in the sand in this area, and I think they've shown some real leadership. Bob made the comment that risk is reduced as the development time is reduced because requirements don't change. I am planning to put that on a poster and bring it to one of my vice presidents and smear it all over the wall. That is a key insight that I don't think too many of us on the airframer side have been really thinking about. And then lastly, Charlie made a number of comments on materials by design. The one I think I got the most out of was this hierarchy scheme. This idea that materials genome supports ICME. I forget what your actual hierarchy was, but leading up to ICME and AIM levels. So I would like to say that among the materials I'm going to be talking about here, semiconductor multi-scale modeling. I believe semiconductor modeling principles can be used to inform some of the ideas the metals community is developing. In turn, I think the metals community protocols, ideas, frameworks, principles can be used to inform the composites industry. I'm kind of sandwiched on both sides. Believe it or not, I do a lot of work on the composite side and the semiconductor side. And why do I say that? The semiconductor industry only ever had to worry about a few materials, primarily silicon. So they had rich data sets to draw upon to validate the models. The metals community is dealing with many, many more materials. Yet they tend to be ordered materials. I think the approaches are much more disciplined in structures. Then you move over to composites, which is a much less mature industry than the metals industry. So the models and the approaches, the structured property development isn't quite as far along as the metals community. So those are some of the ideas I want to leave you with. The last one is, I think you heard a common theme, that open frameworks and data sharing are key. And I think that's going to be a key glue for this whole framework to move forward, including well-defined case studies with well-defined applications. So those are the conclusions. Now let me do the talk. So we started a Nanotechnology Initiative about the same time the ICME study started. It was a joint effort among our 4 product divisions: aeronautics, electronics, space systems, and information systems. And the one thing our director did that was novel and unique for our company was putting modeling and simulation right at the very center of these various IPTs among materials and sensors. We had a couple of IPTs, ultra-lightweight structures, multifunctional composites, and then on the sensor side, we were looking at IR-based sensors and electronics. Modeling and simulation was parked right at the intersection of those 4 IPTs. So what did we do? We took we looked in these 2 broad classes of materials: nano-based electronics, electro-optics, and nano-based structural composites, relying pretty heavily on informatics-based top-down methods, as well as first principles-based bottoms-up methods. So the organizers asked for expository case study of ICME, or materials genome. This is one that came from one of my staff members who was working at TI in the early 2000s. When TI was going from the 135 to 90 nanometer node, Chris on my staff, who was working at TI at the time, sat down and said, we've characterized silicon 5 different ways to Sunday, but no one's ever looked at the effect of the strain tensor on hole mobility. So he said, how would I do that? So he started from first principles, from density functional theory, and mapped the silicon strain tensor to hole mobility, and made a fundamental discovery that if you just simply rotate the wafer a certain number of degrees, say 45, you would be able to take advantage of the process-induced strain in the wafer. This was very, very critical to TI at the time, because they were making the low-power chips for cell phones. At the time, they had about 50% of that market worldwide. They were able to go from first principles to an intermediate level, what we call device physics, up to a circuit level within a matter of months, leading to a first process flow that ultimately led to TI's 90 nanometer node change. At the time, Intel was doing the same thing. They had a 5-horse race between 5 teams. Took them about 10 times more money to develop their node change, with many more wafer mass steps than TI. This allowed TI to capture something like 65% of the cell phone chip market, and that persists today. About every other phone or more in this room uses that chip. Turns out the Intel chip is in everyone's laptop. So this was the flow that he followed. He did a first principles analysis of the strain tensor for silicon, fed that up to an empirical type binding device simulation, pulled out the carrier properties, the hole and electron mobilities, feeds that into a drift diffusion model, which is a bulk model for silicon. It gets the IV characteristics for the bulk silicon, feeds that into a SPICE circuit model, feeds that into a flow mask. And this was all done in a matter of months. So can we generalize this approach? Unfortunately, Lockheed and our friends in industry don't get to work just with silicon. We work with almost every element under the sun. So can we apply these first principles methods to any element on the periodic table, feed that up to some device physics level, feed that up into a generalized experimental design interface where we can now design circuits from materials? These are just some examples of the tools we use. This is not comprehensive. It's vast. These are primarily DFT codes, Socorro, ATK's quantum-wise software. The device physics level, we heavily use molecular dynamics methods, and a code that came out of Caltech called NEMO. And then up at the circuit level, we look at Verilog A and SPICE. So one of the keys is being able to do this rapidly, going from the first principles level up to the device physics level. How do we map very accurate but very expensive calculations at the atomistic level up to the device physics level? This is work that's being done between us and Purdue to develop genetic algorithms to be able to do that fitting, physics-based fitting from DFT basis sets up to type-binding Hamiltonian basis sets. The reason for doing that is simply you don't have all the computational horsepower to handle 100 million atoms with a DFT basis set. You need to shrink that down to something that's manageable for 100 million atoms. So we think this type of mapping could be done for any other for any other semiconductor alloy element. I'm going to skip through these details in the interest of time. This is just one of our favorite codes for empirical type binding. This is types of results we get at the empirical type binding level: momentum, space band structure, real space structure. The bottom line here is, as I said, typical IC contains many, many millions of atoms. We need a simple model that can tease out the relevant electronic structure. I already went through those. DFT is sort of our workhorse down at the ab initio, first principles level. It's very good at doing total energy, ground state properties, transient electron phonon coupling, electronic transport. It's still a little bit challenged for excited state properties and many body effects, such as exciton, van der Waals forces. There's a lot of rich research opportunities in this space for DFT. So we're paying attention to the right side of this list. We've done a commercial integration for the DFT codes with a commercial package called Virtual Nano Language from QuantumWise. And we're in the process of integrating this NEMO 3D code. So here's another what I think is a poignant case study showing the benefits of ICME for semiconductor optoelectronics. How do you predict the performance of a focal plane array, an IR focal plane array, from these first principles, atomic orbitals and band structure? So the case study, this is work that was done over the last 2 years for strain layer superlattice IR sensors. These are just alternating layers of one 3.5 semiconductor with some other 3.5 semiconductor in the roughly few nanometers thickness scale. Very large format IR sensors are the targets, 10 million pixel type IR focal plane arrays, high resolution, moderate cost, ability to dial in the IR absorption cutoff wavelength, which cannot be currently achieved by the standard today, which is Mercad telluride. So here, the approach is basically using type binding Hamiltonians to calculate the band structure for strain systems, looking at hole transport in these very rich heterostructures, combined with non-equilibrium Green's functions to capture the hole and electron transport, optical coupling, and photocurrent. This is just the messy equation that these techniques solve. It's basically focused on, study was focused on designing the absorber behavior, tailorable strain layer superlattice absorption behavior. So the simulation study basically focused on these so-called strain layer mini-bands that form up in the superlattice between one semiconductor. Apologies, I can't reveal the materials because this is considered proprietary. But two different well-known 3.5 semiconductors where if you plot out the exciton wave function for these materials in the strain layers, they're optically active whenever you see these overlaps between electron and hole wave functions. So the goal was basically, the design goal was to optimize layer thicknesses for maximum absorption at some target infrared wavelength. So these are the results. We plot here these two different semiconductors, the cutoff wavelength versus strain layer superlattice thickness, and the absorption strength versus strain layer superlattice thickness. We see two very different effects, leading to a really nice design trade for these two materials. In one case, we see a small impact on wavelength here for the cutoff wavelength. In the other case, we see a large effect. So here, the goal is simply to minimize this particular 3.5 semiconductor thickness to achieve strong absorption. In the other case, for the other material, we see a very large effect on the cutoff wavelength for thickness, large impact on absorption strength, as shown here. So here we trade the second semiconductor for the desired wavelength, through trading absorption strength versus cutoff wavelength. So we found the optimum was choosing a 3.5A thickness that was twice the thickness of the 3.5B. We got our design measures. We could feed right into the grower. We could give this right to the grower. One of the real achievements of this modeling study was our grower would not do another experiment until he got modeling results. And this was somebody who really did not believe in modeling. Challenges ahead, adaptation for other bands in the IR, refining the models for sources of excess dark current, enhancing the photocurrent, looking for refined quantum efficiency, simulation of photogenerated carriers, inclusion of self-energies in the models. There's still some improvements we can make in terms of some of the estimations. I've already mentioned this, the parameter mapping. This is basically the take-home here is there's still some major gaps as you go from these low-level first principles calculations to higher levels, all the way up to the flow masks. At the higher levels, the general interface between the circuit and system level simulation, and the parameterization of these device level Hamiltonian wave functions. At the lower levels, there's a lot of work to be done yet to refine the functionals and scalability for other elements. We have a lot of interest in something called time-dependent density functional theory to give us better, accurate predictions of the transient behavior of the material. So, this is probably about as far as I can get. We've been talking a lot today about frameworks, open, sharing, ways to integrate all these various models. Could we use something like the Google Android Java-based application platform? And I think we saw versions of this in Bob's talk. I think we saw something that looked a little bit like this in your web interface. But could we draw parallels to this sort of plug-and-play model environment from the Google platform or any other platform? It doesn't have to be this one. So I just kind of did a thought experiment. What would it look like for a semiconductor material? You have a system level layer. This would basically be your 13-year-old son or daughter does Java or iPhone apps. There's a million people out there doing this on the web. Have those people work up at this top level for the system design, radar, transmit, receive, SATCOM, flight control, whatever. Component layer is your subcomponents that you build out of the materials. Transistors, lasers, LEDs, whatever. All of these are models for your material. You have model libraries for various material components, whether it be nano components, strain layer superlattices, interface layers, metamaterials, whatever. And then down at the bottom is your workhorse engines that actually do all the calculations, DFT, lamps, growth models, defect models. And then at runtime, you have linkages that sort of make calls between these various layers, just like the Google Android framework would work. You have interface models and multi-scale linkages between models. So say you're designing a seeker composed of focal plane arrays, transistors, mid-wave sensors, ROICs, interconnects. You want to build them out of where you're going to use semiconductors for the absorber material, metals for the contacts. You'll have interface layers. And you'll make multi-scale linkage calls down to the kernel layer for these multi-scale model components. Those would feed back up to interface models, bridging the various components of the mid-wave sensor. Eventually feeds back up into your seeker. So, I mean, I think all of us are thinking, what is the proper direction? I think we saw one case where you start with the application and you feed back to the material. That's, I think, the holy grail. I mean, I think that's where we're all trying to get to for design of new materials. What would that look like in an open framework? And I did the same thing for structures. I'm not going to take us through this one. It's the same basic idea. Okay. So in the semiconductor world, this is a big one, being able to map from first principles to the device physics layer. In the structural world, sort of concurrent multi-scale micromechanics models, maybe even bridging up to 3-level multi-scale models. There's a lot of work being done, I think, in the metals world and the composites world in this area. We'd like to extend these models over a wide range of applications, armors, fluid structure, nuclear and chem biosensors, broadening the materials informatics tools, which I didn't really talk about too much here, to include cost in the analysis. And somebody said, think like a designer. Well, also think like an accountant. You know, when you make every choice you make, when you make a material choice, there's some process choice that goes along with it. What is the cost of those choices? And can you accumulate those like an accountant through your design? Process optimization. And ultimately, we think these tools can be used for product conception and direct generation of IP. So the big payoffs here are inverse design and something we call digital factory, actually mapping the materials design right into the manufacturing environment. So these are just sort of high-level critical needs for material genome and ICME as we see it. There still needs to be a lot of work done in the foundational computational methods at the DFT level, at the intermediate levels. Something we would call recognizable meta workflows for certain classes of materials and applications. Open interoperable frameworks allowing us to automate. And I think a couple of you referred to standardized interfaces, standardized security protocols. All of that is needed. And then something I call precedent-setting analysis cases. And we've seen a few of those. We saw a few of those from Charlie. And I think they're out there. I think a lot of them are coming from this community. A most prominent one came out of Los Alamos National Labs recently on multi-scale modeling of nuclear reactor metals. The precedent-setting cases are happening, I think, right under our noses. We need to be able to draw upon those to help define and replicate those workflows. So the summary, this is sort of the motherhood statements. We continue to look for affordable, flexible materials and manufacturing solutions. We still have a very strong case for MGI and ICME. As someone said, we can't walk away from it now. It improves our overall competitive position in the global economy and national security. We are at a crossroads in our discipline. Modeling is rapidly catching up to material science. We see computationally driven materials development and manufacturing emerging quite strongly over the next couple decades. These are just the many people that were involved in all this. Thank you.